everybody. So this is Jatin Kumar. This is your first lecture on Linux system programming. So I'll be covering basically three modules. This is for the program is designed for who wants to actually have knowledge in how the embedded systems work and how the system work. So basically, even if you see embedded system is nothing but a system with hardware and software integrations, right? So I'll be actually covering in depth how to deal with the different systems. So we have divided my course into three modules. The first module is programming essentials, where we discuss about the user space application of the program. Second module is the kernel programming, where we discuss how the OS provide, what features the OS provide, or how we can use the feature in to do our programming. The third module is deploying on hardware. So we'll be actually practically deploying a kernel. We will port a kernel into a particular hardware. So the prerequisite you should understand C. So if you do, that's better. If you don't, I'll briefly tell you something summary. So starting with the course, so I'll briefly tell you what you do while you compile and while you build. What is compilation, what is build, and everything is covered in this topic. So I say, so this is what is kernel inside. So the kernel, if you see, the kernel consists of a underline is your hardware peripheral, right? So the application you work on, whatever you have seen on different application working on languages, is above the system call. So above the system calls, there are is this is only the kernel space is there. Above the system calls, the user space. The kernel space consists of the process manager, SSH management, IPC file system, device driver. So all this I'll discuss later. So first of all, I want to discuss these things to you because this is very important as a system developer, as a C programmer. If you know these things, how the compilation take place, what are the stages involved. So actually, if you consider from the bottom, so the everything it boils down to is binary, that is 0 and 1, which is actually understandable by the system, right? And above the binary, if you are an engineering student, you might have studied an assembly language. So there is something called assembling language, and which indirectly turns an opcode to a binary machine level understandable form. So do we write assembly file, or do we actually write assembly language? No. So we do write different languages like C++, Java. All these languages internally, what it does when you compile and where you actually build an executable image. The executable image is nothing but a assembly language format. So the assembly language level format, they actually have converted into the binary file, right, after linking. So these process I have to discuss in detail. So first of all, let us do practically and understand what is doing inside. So in practically, so we have Linux operating system here. So all the things we do here is all practically basis, right? So here you see when there is a file called 1.c. So I'm looking at the file 1.c. So this is a simple C program, all aware of it. So I'm just included a header file, which is not necessary to include this header file. Very important. The header file inclusion is only for checking the parameters of the function, taking the prototype of the function. That's it. If you don't include the header file, it will also compile. So this is the main function. In the main function, I am calling a print function, which is I am printing the string welcome to my class. So that is what I am doing. So I'll be dealing with how this is converted into the zeros and ones of the system. So what steps are involved in it, what what does each and every steps is an important one, right? So here you see. So this is my present working directory, right? So vi path 1.c, which for showing the 1.c, right? Now what I do is I'll compile 1.c to 1. So this is done. So what is 1? What is 1.c? So if there is a tool called file tool, which is tell what type of file is it. So if I see 1.c, so 1.c is a source file, which is very important. The name itself is very important. Is a source and is a ASCII text format file. So if I see file 1, so what is it? So is an ELF 32-bit executable file. So it is a executable file, and it is Intel is a processor independent file. So it's compiled for Intel i386 processor. And what is this v5 is an ABI. So I'll discuss these topics in detail right now. So first of all, this is the what does the steps involved from this source 1.c to the output 1. So there are different steps involved in it. So first of all, we'll look at all the steps. So first you see, so there is a source file. The source file is 1.c. So 1.c, after it is a preprocessor converts 1.c file into preprocessor file. So we'll see how it does it. So GCC, if you mention -e flag, so 1.c output to 1.i. So .i is just a convention, you can mention any name. So it will convert 1.c into 1.i. So what does the 1.i contain? 1.i. So as you are viewing, 1.i contains many more things, right? So this is your function main. About that, what you have written, hash include stdio.h. So it has included all the functions prototype which are included in stdio.h, right? So it has resolved. The hash is a preprocessor directive. So what does the preprocessor directive does? The preprocessor directive extends the file. Tell the preprocessor to include this file also. So this is the stdio file, contents of all the contents of the stdio file. Now what it's internally involved is very important, right? How this file it come. So for the internally what type tools it is using, I'm going to verbose this step. So after verbosing, what is important? So what does the GCC doing? The GCC is now with the -e flag is going to a specs, there is a specification file where the where your GCC is there, where your path is there, GC path of the compiler is there. So there is a, where the toolchain is installed, there is a specification file known as spec. So it assessing this particular specification file, right? So what is collect GCC is verifying that you are calling GCC, so it is verifying it here. Now it is compiling for which target is it. So it's a x86 based system. So generally, so our system is a x86 based Intel architecture. So according to this architecture, it is compiling the particular file. So what does this configure with means? So what does this mean, configure? The main thing about the configure with is it verifies which are library needed for this 1.c. So the 1.c is dependent on which library. So all the library are present in your system or not. It is verifying that here. So configure with is verifying with. Now now the next step what is doing is, so as you see, so the next step your, this is what it is doing. So cc1 is nothing but a preprocessor. So it is the location of the preprocessor here. So it is compiling the, it is invoking now this particular spec file that contains script. The scripts is invoking one preprocessor here. So the preprocessor, and now the output is 1.i, right? So is the architecture is i386 based architecture. So now few more option it is also passing. Now what next it is doing is, so next it is trying to look for a location in header file. If you are able to see what next is, now it's trying to look at the location of the header file, where the header file is, right? So now it is, so the now it is including that header file, attaching that header file to 1.c, and the output is 1.i, right? So this is what is internally done. So if I repeat, first of all, the GCC goes into the spec file of your toolchain. The spec file contains a script that runs. In the script, what it invokes is, it invokes a particular, it 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 first of all it checks whether the particular library is loaded or not. So if it is loaded, if the architecture, what check that, what, how it is compiled, what type of tool is used, it verifies the tool, it verifies the libraries, and then it goes into the cc1 preprocessor. Then the preprocessor attach all the header file which are necessary for it, which you have included. So this is the first step which was saying. So first step is the source file converted to preprocessor file. Now the second step, the preprocessor file converted into an assembly file with the help of a compiler. Now how it will do it? GCC minus C is for compiler, right? 1 dot you can actually you can mention either 1.c or 1.i, because it will it is backwardly whatever files is there input file, the script will take care. So 1.i and last file output to 1.s. so if we can see, there is a 1.s file. So what is the type of file? 1.i is also a C source file. This is also a source file. Now what is 1.s file? 1.s. So what is 1.s? 1.s is a executable 32-bit file, right? So just a second. If you want, I'll have to just not directly do an executable. I have to first compile. So -s is for compile. Now if I see 1.s, now if I do a file with 1.s, so what is assembler source text? Now it's also a source file 1.s. If you are able to see, sorry for my previous actually I've just done directly last step. Okay, so 1.s, what is 1.s? is assembler source text. This is also a source file. So what steps are involved in this? So if you find out the steps, I am doing verbose. -v is for verbose flag. So if you are able to see, so the same things happen. The same, the config, it verifies all the entries, it verifies the library also, and also what, and the last, what the difference, if you may see, the difference you may see is, so it is doing cc1, the same preprocessed 1.i is now compiled to, is a source now as a cc1 is a also a tool. Now cc1 is actually what it does is it converting the high level C level language to a machine level assembly language conversion. So compiler, what it does, so it compiles a high level language to the assembly language low level language. So this is done by GNU C version compiler. GNU C version and the compiler is this, right? So as you see, now 1.s is there. So what is the content of 1.at? If we see, very important. So what is, so this is file 1.s. this is RO data, means read only data. This is string. So welcome to my class. This is text section. So actually assembly level file, you see there is a different section basically. So text section is different, main section, stack section, all the section are included in it. So what it is doing, so this is push L EBP. So push L is nothing but assembly language, whereas EBP is a base pointer, right? So there are two pointer in x86, base pointer and stack pointer. So base pointer pointing to the stack frame, to the current base of the stack frame, and stack pointer point to the top of the stack. Now push L, what is that? It pushes the base pointer to the stack pointer top. Now what is doing is, now finally after pushing the base pointer, it is storing the value of the base pointer into the stack pointer for the return address, right? So and now if you see, finally after doing cache addition, means populating the cache, now it is calling a routine called printf. So the call is call routine. Call is an assembly level instruction to calling printf. So do we see here printf code? No, the printf code is still not here. It is calling the printf function. So this is only an 1.s is nothing but the source for assembler, and 1.c is source for compiler. So compiler has converted 1.c into 1.s. So this is that part. that is preprocessor file is converted into assembly file. Now what does assembler does? Assembler does convert assembly file into a relocatable binary file, right? So what is relocatable binary file, we will see here. So assembler what does, so we'll invoke now an assembler. So AS is an assembler, or we can GCC, right? So this is invoking, trying to invoke an assembler. So to do this, we are doing gcc minus c 1.s minus o 1.o. So as you see now, what is 1.o? So 1.o is a relocatable ELF, is an ABI executable from is executable linkable format. So and is an i3, it's compiled for the i386 is my architecture, and is sys v5 ABI, right? So what is ABI, will discuss, I will discuss in more depth. So now what does the file content, let me show the file content 1.o. so I'm not able to here show, because now the 1.o is a relocatable file format. So for vi doesn't show it, so different file format. So every file format has its own headers, so vi don't support. So we do different tool called objdump 1.o, right? Right. So what, so setting minus d is for disassemble, disable assembler contents of executable section, we have to do this. So objdump minus d for flag and 1.o. so this is the disassembly of 1.o. So from here we started. So disassembly, if you can see the section, this was what does the compiler the source, and now what this assembler does, the assembler convert this instruction into suitable opcodes. So these are the machine level opcodes of the this instructions, right? So this is main. So if you can see, so the printf, the call to the printf is replaced by this is, what is this? So this is the, and still the code of printf is not here, so very important. So actually the printf is in library, which is std, it's a printf is a library, libc library. So the code of the library, so the library is shared library, so that it is actually passing the address of the shared library. We'll discuss later what is shared library. So here I am just giving you overview of what is happening inside. So disassembly, now you here is the opcode, and what is this 0 1 and 15 and 16? So 0 1 3 6, so this is the logical address where this code resides. So this is the data and this is the address. So 55 is the data and 0 is the address, right? So the address, every address starts from 0. So if in your process every address start from 0, all the process will corrupt, overwrite itself. So it's not a physical address of yours, it's just a logical address. So now what do you mean by relocatable? So very important, the concept of relocatable. So the relocatable actually is a process specific address, is not an address, your address space specific. That is, means it actually means it is the process space address is 0. Okay, that your call is offset, printf is offset 10 from the process space address. Okay, but the load address is not yet decided where it actually get loaded, right? So assembler output you have seen. So I have not done verbose, right? So we'll also do a verbose over here. Minus v, what tools it is invoking. So as you can see, gcc is invoking an assembler. So what is the assembler? As is the assembler, this is the command. So as minus v. So what is the version of your assembler is installed is 2.4, right? So internally what it's doing, it is doing the same, it is verifying all the whether library is there, and then it is invoking an assembler as. Now the assembler as is converting this 1.o into 1.s, that is this part, assembly language, into relocatable binary format, right? So now there is a very important tool called linker, which convert relocatable binary format into executable binary format. So how it is converted, we'll see that. So so the process from here, relocate from relocatable binary, conversion from relocatable binary to executable. So this particular process is called build process here, build process. So the word you have, the build, comes from the linker. So the linker does build process. So gcc 1.o minus output to 1. So if I t file 1, so file 1 and file 1.o, so you are seeing any difference? So is a executable and this is a relocatable, right? So it is a dynamic link, use shared library. So now this, what does the 1.1 contains, and what you have already seen 1.0. So what I am doing is obj dump 1. So obj dump is also a tool which can show, which can disassembler that. So when I do obj dump minus d 1, so obj dump p, right? So now what are you able to see here? So there are lots of code also added. Your main function is, where is the main is here, right? So now this logical address is converted your address space specific, your processor specific address, right? Now this address is where actually your program will reside. So now it has converted it into this address. Now what else it has done? Very important thing. So notice what all the other things have nickeled. So this all the other function it has added. So you are able to see, so underscore start function, right? So which is calling is your c underscore main, start underscore main function, right? So this is the another printf function here is here. So right, so this is what is it. So you are able to see. So what is the underscore init function? So some of the other function it has attached. So linker, so now what is linker doing? So we'll see while verbose it, right? So this is what we have done, minus v. So we will see linker is here. mm, ld, I think it should be your linker. ld dot so dot 2 is your linker. Alright, this is minus c option left. So somewhere you will find this ld as a linker. Now what is important is what is doing, what is actually does. So and so you see any difference from 1 to the 1.c. If I see to two files, I'll compare the two files. Dump 1 dot o obj dump minus d1 dot. So these are the two files. So now if you see the main function itself, what else has changed? So it first instruction is push ebp, move, subtract, call, leave, return. So all these are there. So it has also added some of the all more instruction to the main, right? So what does a linker do now? Very important. Just think about it. What else has been changed? Look at it. Right? So what does linker do? So the linker, first of all, the call to the this call is also replaced with this address. If you see this call, this address, push, move, call, leave, return, all these are there, right? All these are here. But the call to the printf plt is nothing but your procedure linkage table. So it resolves the virtual address into by a processor linkage table, by verifying a processor linkage table, and it has given the address of the printf function, right? So now this address is who gives this address, very important. Just think who has given this address. So the memory manager has given this address. This address is now the memory. This has been a system call. Now what? Memory manager has given this address. Yes, memory manager is a subsystem in the kernel. So now this memory is a stack frame, the stack pointer, and the stack register is a processor specific or not, right? So now if it is processor specific, now all these commands has to be processor specific. It is not Now this particular file is also a process specific. If you move this file to the Linux system or to the Windows, from the Linux system to the Windows, it will not compile. So so first of all, what the three main things the linker has done. So linker has converted an executable binary to an from a relocatable binary to an executable binary. First thing, instruction are mapped to an offset address. Second thing, each function is referred by offset position. And third thing is runtime libraries are also added to the function, right? So so what is runtime library? What is library? Very very important. Library is a set of routines which you don't need to write every time, which are already there. Alright. So so the runtime, now the runtime code is a contains two things. So this function is also contained along with all these other functions, right? So now this all these other functions along with the runtime code, now these functions are called executable code. So all it is this called ABI of an OS, right? The ABI is nothing but a application binary interface. No. Now what else you are saying? Very very important. So you are seeing when I application, what is this Fini, and what is Fini? Very very important. And what is this function called init, underscore init? So underscore init is the first function to be called in the init. What is in underscore, what is the responsibility of init function and finit function? The responsibility of init function is to populate the stack. Now after populating the stack frame, the actually each function has its own stack. Main function also has its own stack. So the underscore init function populates the stack, talks to the memory manager and this frame. And underscore init deallocate the stack. Now underscore init function calls start function. Now the start function now calls main function. So if you want that your main function should not be the first function, you can also change that. So this is a myth that main function is always a first function. So main function is by default a first function, but you can change by using a hash pragma. So hash pragma, in it you can change the calling of the other to your own function. So it's not that the main function should be the first function, right? So 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 this is what a runtime code is. So if you want to write something, you can write some definition of the runtime code. So what the runtime code is, runtime code is an executable code dot o plus some more functionality, underscore underscore init, underscore underscore start, and underscore underscore fini, right? So the what is the responsibility of runtime code? So if you can mention that runtime code responsibility is to append the stack. Runtime code responsibility is to append the stack and add resources which application needs to run, and add resources which application needs to run the first piece of code to run is runtime code, and it is run while loading. When application get first call runtime code. So this is also called a bootstrap code. So this is, if you have noted down, we can move further. So now you understand what is runtime code and what is executable code. So now you have actual address where your program will get loaded into it, right? So what does the so is that runtime code? So what I am telling is the runtime code is processor specific or not? Yes, it is the processor specific. Why it is processor specific? Because these addresses are, if you are seeing these addresses, now these addresses are a processor specific address. Now it talks with the memory manager of that particular processor. So if it's talk to the memory manager, so talking to the memory manager is nothing but doing a in kernel space. So in kernel space it can only call a system call. Through system call it can only talk. So if it's calling the system call is also responsible now to talk with the memory manager subsystem of the kernel, which actually interacts with the memory manager. Now the memory manager tells that the stack segment of your particular is this one. So the it acquires stack segment. The memory manager gives now stack segment. So now this is not an operating system specific. So if you want your application to be portable, what you will do? Very important thing. So if you want, suppose you have an executable image, you want it to be run on different application. Now what do we do? So you have to separate the runtime code with the functionality, the core functionality, and that's what the JVM does. And in the C version, we have also a C version of it called C#. So they remove the runtime code and make it as a software. So now the core functionality is now portable, right? So what is now an ELF format we'll discuss in the next lecture. Thank you. So if you want, you can run 1. So what does the dot slash does, we'll also discuss in the next chapter. We'll discuss. Welcome to my class. We'll discuss how this dot slash 1 does and what system call it makes and what internally it does. Thank you.